Thanks, great to be here. It's the first time I'm at Bob. So this is the title. So and it's actually a very simple story, and that's actually the hard part. It's all very simple in the end. Programming joins efficiently. So this is actually me, and I just want to point out that I'm from the university, but I've actually been involved in a number of startups and a couple of. It's all small things. Actually, some of them are actually growing quite nicely. Actually, it's kind of fun starting up a whole university. So this was actually the most successful and biggest startup I've been involved in. So, okay. So first of all, rules of engagement, just ask me questions, okay? We're not like 300 people here, so, and I'll just adjust my slides to be sure I'm going to be finished, okay, by the end of it. So a very common programming problem is like you have a list structured data. Maybe they're just streaming data. They're coming in from the network, or you're reading something in a streaming fashion, which is not so unusual. Or you might have lists in your program, right? So, and you need to join them. And I'll keep that informal for now. So in the sense, like you have multiple sources, you need to join them to get some combined information out of this one. So like classic thing would be the top salespeople of wool sweaters in Iceland. Okay, you can already say, oh, maybe there's probably 3 tables involved. Or, and I'll use this one, is like you only have a single table, so it's a self-join, where you say, like, I want to have all the triples of friends such that, where X likes Y and Y likes Z and Z likes X. It's like in a triangle. And so what do you do? So what do you do in practical programming? I mean, apart from what I did yesterday when I redid this, I asked Claude Code, of course, how to do these things. Was very good, actually. So you employ a library for filtering, projecting, joining pairs of lists, okay? So you say, I have a library for putting these things together. So in particular, the joining part, and I'll use that. Or you say like, well, we have about 50 years of experience with, well, not quite, but 40 years at least, experience of writing SQL code. So we'll just do, or, some kind of query language. And there's like, dozens of years of getting this to be done efficient. So I'll just write in that language and dispatch it to some kind of SQL engine. People have worked on this forever, so hopefully that'll work. Or you code it yourself. You could say, how hard could that be? Okay. Actually, let's look at that, okay? So the first thing is like, first of all, what is joining? And so watch out, I'll have some slides with quite dry stuff, okay? So, because I want to step back, what does it mean to join, okay? So, and if you're from the database, who's a database programmer or, someone working with database programming? Okay, cool, yeah. Well, how could you avoid it, right? So it's like, do this and try not to use an RDBMS. Oh, no. Okay, so I'll give you a slightly different version. So who's actually heard of first-order logic or predicate logic? Wow, this is, I don't know, I must be in Germany now. So, okay. So, what is a relational query? Well, it's an expression of the form where you output this k-tuples, and the k-tuples of variables are the ones that are free variables in a formula. The formula is a first-order formula, okay? It doesn't have function symbols, that's why it's called purely relational. But that's basically it, okay? So a query maps input relations to an output relation because in that formula there will be some relation symbols. That's the input. And then they get actually, we define actually which are the tuples here that yield true, and that's the ones you want to output. Quite abstract way of putting it, but it's actually not too far from those descriptions of relational calculus you usually see in a database class. So what is a conjunctive query? Well, that's a special kind of formula. So we're restricting ourselves to a certain formula, okay? And that is a formula where the phi is built from only the relation symbols. That's always, we have that. That's the input. And only conjunction. And we can also use an existential quantifier. And the free variables have to be exactly, free variables of this formula in there have to be exactly the ones I'm mentioning here, okay? So what is a join query? Well, it's the same thing as a conjunctive query. You're just not allowed to use an existential. An existential might be confusing, but it's basically just a projection. Projection means like, leaving off some of the variables you otherwise have. You're just returning the tuples without those. So let's look at an example. And as mentioned, we'll have a running example, or 2 of them. So we'll represent a directed graph by a binary relation. And as a universe, you use anything at all. So I'm just using the natural numbers now. Or you can think of them as strings. They can be multi-sorted. So it's not important. Think of it as the attribute domain, okay? And so I will say like, okay, I'm interested actually in these 3 tuples, which are only paths, namely of x1 to x2 from x2 to x3, right? What does it mean? To express it in this formalism, it means that, well, there has to be an edge from x1 to x2. So x1 and x2 has to occur in the relation. And an x2 to x3. Great. And x2 is repeated here, as you can see. So we can see that, oh, this is a path from x1 to x2, x3, okay? That's one way of expressing it. So we can go one step further and then do the thing we said before. The triangles is like basically the same thing. It says like it's just more additional constraints. x1 to x2, x2 to x3, and x3 to x1. Okay? So now we got triangles. In SQL, you could write it, for example, like this. This is the canonical waves. Select all the first components of my relation. So I'm saying like this is self-joint. So R1 stands for R, R2 stands for R, and R3 stands for R. And then I'm just taking the first components, call it x1, x2, x3, corresponding to these, and then making sure that the second one is, oh yes.
On the previous slide, why don't you allow projections? I mean, it's like writing some fewer expressions after the select. Is it important?
No, in this case it's not important, but you could actually ask an even tougher question. I'll get to it in the end. Why do I only have conjunction in here? Why don't I allow disjunction? Why don't I allow universal quantification, not implication? Why don't I allow negation? All these things are actually possible, but they make the query processing harder, right? So we'll just restrict ourselves now to join queries.
If I know that I'm going to project something today, then it could be easier to evaluate the query, because then I can stop looking if I have just one witness.
Turns out it's not much easier, but you're right. Absolutely possible, because you're duplicating some of the effects. You're calculating some things. The funny part is actually that SQL has a multiset semantics. They actually can't do that. You have to account actually how often you're projecting it out. So it doesn't really make exactly the projection part doesn't make much of a difference here, okay? But other parts that I mentioned, yes, thank you. That makes, so let's just stick to the join part. So how do we execute this? So this is Python, okay. So if you guys expected Haskell, ha! So the triangles, I will say it's very simple. We'll just build them up by collecting all the x, y, z. All we do is we just have a nested loop. It says like go through all the tuples in the relation. Well, x1, x to xy, and then do it 3 times, okay. And then just checking if for the matching pairs from from xy to only if they're matching, we're actually going on and getting the other ones. So the checking then is like, oh, we're adding the ones where the z here is the z2, and where actually the x is the x2. So basically, we're just enumerating these things. That's wonderful code. I highly recommend it for testing as a specification, because it's very hard to not write it correctly, okay? So what does it do? So let's look at some data sets. They're not accidental. I'm kind of cheating here. I'm giving very hard data sets, very easy to describe, and very hard data sets for classical database systems, okay? But let's look at this parameterized data set, which we call the Alice set. So Alice is number 1. I don't know, only a mathematician would say these things, but okay. So Alex likes everybody, Alice likes everybody, and everybody likes Alice. That's our pair, okay? So we have n people, including Alice. So, and that's the binary relation we'll be looking at, okay? So, and a little bit of thinking here, and actually, you will find out that the number of triangles we get from this one is not a lot, okay? So it's exactly 3n minus 2, okay? So there's 2n pairs in there. So n is a number, it's like, I don't know, 55. Then we have 110 edges here, and then we have 163 triangles. Okay, so, all right, so let's look at some execution times. Beautiful, simple code. And we can see that, if you execute the code you've seen on, like 400, 800, and we get that we have, this is the right, should be the right, no, okay, so this is the number of triangles, and yeah, so this is the number of edges. So we get that this runs on my machine here. This is a 5-year-old Mac, on M1, 16 gigabyte, whatever. Yeah, so it runs 42 seconds, okay? So you can see actually from this development, I can only recommend actually looking at these things always like by doubling the input, okay? And then actually then seeing what the factor is on the outside, so.
Question.
Yes?
Maybe I missed something.
Yeah.
So the Alice set looks like more like a star. I would say there are no triangles, but I'm obviously not understanding something. So everyone likes Alice. Alice is in the center. Yeah. Everyone's around it.
Yeah.
There's a spoke on
Yeah.
everyone.
Yeah.
And so there's this relation that's, but I don't see any triangle there. Where is the triangle?
Oh, the triangle. So what would be a triangle? Yeah.
Alice is twice in the triangle.
Pardon?
Alice appears.
Yes, exactly. Yes, yes. So you could say a triangle is, oh yeah, Alice likes everybody, including herself. Okay. So so it's like, you could say like, Alice and then anybody else really, that's a triangle. Okay. Yeah, that's it, because, the third person likes Alice again, right? So, so this scales with cubic time. Shouldn't be entirely surprising, okay? So it's beautiful, simple code, as I said. Don't underestimate the value of that. It's hopelessly slow, okay?
Are reflected triangles different? Because if they are not, then permutations don't count as different triangles, and then you don't have 3 and minus 2.
So yeah, so triangles are defined as they are. So if you want to have them in, yes.
Alice, Bob, are they the same or not?
No, they're not the same, because by definition not the same. So if you want to apply, actually, you can easily see them, and you have to divide it by 6 because you get all the rotations multiplied. You can do all kinds of things. But right now we're just computing that set. So think about it this way: you're writing a query, and the query is not, first analyzing that this is actually a rotation insensitive query. Okay, that would be an interesting optimization. Okay, so. So this is just, an example of a query, a triangle query. Okay, so let's take a little bit of dictionary-based approach. This is it's a dictionary-based join. Usually people call it hash join, even though you don't have to use hash tables for that. So you say first we build up a dictionary here, and the dictionary just means like for every x, we'll have the set of all, and we have a very efficient data structure, the set of all adjacent neighbors. Okay, and then we just say, for all the x in D, this is Pythonese for all the keys in D. Okay, so which means like, a dictionary has keys, and then, the corresponding values that the keys map to. For all the keys in D, we'll look at all the neighbors of the keys in D. And then we look at all the neighbors of those, the y's. So we're going from x to the y's to the z's. And then we check, is the thing that we started with, the x here, is that actually reachable directly from the z, the last one? Z is the x3 part. And then if it is, then we append it, okay? Is that okay, code? What do you guys think? No? All right. So let's look at the numbers. So when you execute it, Python 3 standard thing, you get we get quite a bit better things. Remember, this one was already 40 seconds here, right? So we're at sub-second, and you can go up to 2,800 and spend half a minute, okay? So if you look at this one, you can see it scales with quadratic time. That's probably as good as it gets, or is it? Why not? Or, yes?
Maybe the symmetry of the problem is not being exploited, maybe? I don't know.
Symmetry will only get a constant factor, yes. Yeah, but that, yeah, good. With that, okay. So yes, it's basically symmetry you were alluding to, right? Yeah, yeah, but it won't help with the asymptotics, okay. Yeah. By sorting things first. Turns out you can't. Yes. But that's a good idea, because you usually sometimes say, let's sort it and then do a sort merge join, right? Yeah. So basically, the Alice has the following problem is that we, in the first step, we find all the neighbors, and in the second, all the neighbors. And if you take the transitive closure, though, that's n squared number of edges, okay? And these get computed. Or at least you iterate over them, okay? So the time is going to be quadratic. So I'll allude to that later on. This is actually one way of illustrating this, a proof that says no query optimizer that most of you have learned in database classes that are sufficiently long ago can actually get anything faster than quadratic time, okay? Let's check that because, there is some clever database systems and there has been research in the last 15 years. So let's do this. So let's look at Postgres. So, okay, Python, load Postgres, execute these things, and we'll see that it executes, well, 3 times slower, okay? Still scaling the right, what looks like that's the way it is, okay? Remember, actually, the output is linear, but the number of steps we spend, and the input linear is quadratic. Yeah, man, Postgres, that's like using, I don't know, it's using a huge machine for, a very specific job you have at home, right? So, and it's running in its own process and servers and all these things. Let's use an in-process query executor. Let's use SQLite. SQLite is actually fascinating to watch. It's gotten from being a very simple-minded database engine to actually a very, very, very good one, okay? So what does it do? Well, that's not so bad. 64 seconds, okay? It's 30% faster than Postgres, 50% slower than the Python code we wrote, okay? But we get a sense that that's basically what it does. It figures out in the query engine that it executes the code that corresponds to what I've written down with the code. And so, some of these engines still have to be told to build an index, which means a dictionary. But that should be automatic. And that is automatic here. So now let's look at DuckDB. Who's used DuckDB? Okay.
What's this in memory or what is it?
So this is in memory and in process, which means it's directly accessing data. And the engine basically works as a subroutine, okay? While with Postgres, the main difference is that's the server, so you have to ship the data over via inter-process communication. But think about it. The data sizes are tiny here, okay? They're really tiny. A couple, I don't know, 20 kilobytes or something like this. This is like, boom, like, it's not even that. And also coming back takes no time, right? But still, it's running its own process. So DuckDB. Well, I mean, I talk to database people. I'm not one of them. I say like, well, that's the thing, okay? That's going on. Very active develop, very new results recently, and added very, very clever techniques. So if you look at this one, it runs in, well, 7.8 seconds, but you can continue running it for a while, much longer. And you can see in the beginning, it's actually starting very slowly and linearly, and then it's kind of switching over into the 3 halves. So it is asymptotic. Well, we should continue here to see whether the regression still works, but it'll probably work. It's actually a little bit unclear because from the papers they have. But it looks like, it's definitely scaling much better, right? In 3 halves. We just said that's not possible. I mean, it's not possible with classical query optimization, which is like finding a join plan, okay? So let me at least say there's no contradiction. It just means that that's not the way they execute and evaluate a query, okay? So, but there's a recent paper at one of the primer conferences that shows how to do this. They don't claim to have what I'll call later, what is called worst code optimal, but it looks really good, okay? Let's try one last thing, and that's what the talk will be about. Let's look at this piece of code. So triangles starts off with a dictionary for the first. Remember, the triangles was, R has to be X to Y, and then Y to Z, and then the same R. For each one of those occurrences, we build a dictionary, just systematically. For the second one, we don't need a new one, so we'll just use the first one, okay? So this one, if you look at this one, is actually a dictionary of the inverse relation, okay? So This dictionary is just what we had before. You point to all the neighbors to the right. And this one is a dictionary that points from the right to all the neighbors to the left. Okay? Now, we initialize it, and in the end, we put some x, y, z's in. So, and then it's just a nested loop, okay? X, Y, Z, and here's a Z, right? You saw before there was also a test. And the Z, that's a nested join loop, right? So, what have we all learned about nested join loops? It's like, that's like the first one. It's like, that's not going to run fast, okay? But there's a couple of things in there. There's this min set in here, and min set, and otherwise, and the y's are a little bit, so x, y, z, so it's the x1, x2, x3. So it looks like a dictionary-based join bit like before, okay? And it's simple and quickly coded. In fact, I'll show you a recipe. You can just write it up. But the question is it efficient? Yes?
Could you please tell what min set denotes?
Yeah, so absolutely, I have to say that. So what does it denote? So here's the definition. So this is the total code, okay? This is everything. There's no special libraries used. This is standard Python. So the first one is really just a way of building a dictionary. It's just called dict2, slightly different, but it's basically the same thing as we've seen before, okay? And min set is this very complicated function, okay? It says if you give me a set, which could be the keys in a dictionary, right? That's a set. And two of them, what it does is it asks the first one, how big are you? What's the size? I don't know, it's called length in Python. Do not ask me about these things. So it asks, how big are you? It asks the second one, how big are you? And then it says, I'll return the set that is smallest. Okay? Okay? Let's just go back because it says here that we have to basically iterate over the keys in R1 and R3. Okay, that's basically what it means. But what we'll do is we'll first check who's got the most keys. And we'll use the one with the least keys. We iterate over that. And in the other one, we just check whether the key occurs or not. Okay, and that's what we have a dictionary for. It's quasi-constant time. And yes. Okay, so this is total code, everything, nothing hidden, okay? 25 lines. So this is actually performance of this code. So we're down here at 0.024 seconds. You know, we ran this in a day of 10 million, okay. Yes? Yes? I'll show you the code in a different version again, okay? So, and I'll go over it again, okay? And I'll show you also actually how it came about very systematically, okay? But yeah. So, all right. So now these are the combined numbers that I've just shown you. And maybe we show a log-log graph. So remember, this is a log-log graph. So the steepness shows us the exponent, okay? So, and there's also absolute numbers, of course. So you can see here, DuckDB, clearly better than all the other ones. They're quadratic. But in absolute terms, and in the kind of, you can't see it quite, but it's growing faster than this one, okay? And this is the code I just showed you. So, okay. And, I don't know. I don't know. That's strange, isn't it? So, what's going on? So, So that's the second half, or that's actually the real talk now, okay? More dry stuff. I have to say, what you've seen here is actually what's shaken out of some stuff that I'll allude to at the end. Just we shook it out of something more general, okay? So, and shaking out, I mean, it's like leaving out a lot of, what is it called? $1 words, okay? So, an algorithm for computing join queries is worst case optimal. This is the definition. If it's basically linear in the size of the input and output. But it's open whether these even exist. So there's a weaker form of being optimal, okay? And by linear, I mean is in the sizes of the cardinalities of the input relations and output relation, okay? So I'm saying like well, it's not me. This is the definition. It's linear in the size of the input, the sum of cardinalities of the input relations. You have to read all the input relations. How could it be faster? And plus, you have to output something too, right? So plus the size of the largest possible output relation that could be generated from inputs of the same size. Okay. So it might be that the output relation is actually quite small, could be empty even, okay? But with a different equally sized inputs, we could have generated much bigger output, and then we say it's okay for an algorithm to use as much time as reading all the input plus as printing the largest possible output. Okay, so all right, so a big question actually until about 2012, do worst case optimal algorithms even exist? Because it turns out it can be shown that no select project join query plan, so that's the one I alluded to, can generate a worst case optimal algorithm, okay? So it's got to be, if it even exists, they have to be generated differently than just by our textbook knowledge of query optimization. Okay, so let's look at largest possible outputs. Here's some examples. With P3, okay, so there's a standard algorithm, basically we just iterate over it and then we output x1, x2, x3 up there. So it turns out that the largest possible output for P3, if the input has n edges, now I'm writing capital N edges, distinguish it from the number of nodes, remember it was a lowercase n. So that's O of n squared. You can think about it, that's what Alice actually gives you. x1, x2, x3, and how many of these triples do we get? N squared, okay? And it turns out, this might be coming as a surprise, that if you add this extra constraint, it's not just that some of these values x, y, z, remember in the z means that you also have to point to the x, that some of them get thrown away, almost all of them. So at most, n to the 3/2 survive. That means that the output of this triangle query is much smaller in general than of a path query, okay? And worst case optimal basically means that, now we have less time to compute it because, the worst case output is only this. So can we find a worst case optimal algorithm? So, and think about it intuitively, where the time is wasted in principle in the classical algorithm is like, we compute a lot of intermediate data. Remember these n squared triples, and then we filter them out, and only a small fraction of them get into the output. And that filtering, that production and filtering cost enormous amounts of time. Yeah, who's heard about the AGM fractional edge cover bound? Okay, I don't know, but beautiful results, okay? And they really, really say a lot, okay? And actually, they're actually being used in research databases now, okay? So, and there's been a number of works where people discovered that things worked faster than doing it by the standard optimization of query processors. All right, so, and if it seems like, whoa, okay, and the DuckDB is not even known to be worst case optimal, probably is not. So this seems like, it's very difficult, isn't it? Very tricky. So it turns out, we call our algorithm simple join. It turns out that you need the following ingredients and only these ingredients, and you will end up with a worst case optimal join algorithm, okay? Which is, you need what I call nested dictionaries, because remember you have, from X to Y and from Y to, there could be a relation has 6 attributes, right? Then you need a nested dictionary, which is like from X you get to a dictionary containing, the next one, the Y, and then from there you get into a dictionary that takes the Z, and at the end you get a truth value, yes or no, I'm in there, okay? They have to have the following thing: constant time length. This is very important. If you ask a dictionary and say, how big are you? It has to be, say, 27. It's simple to implement. It's dead easy. It's amazing that many data structures do not implement it, okay? So you just have to do it yourself if it's not there. Then you have iteration. You just iterate over the keys. That has to be done constant time per key. And lookup has to be quasi-linear. Okay, so basically constant time. Okay, they give you a value, you give them the result back. It says that's what it maps to. And you don't need a support for element deletion, addition, merging, or other operations. So you don't need to support, have a data structure that does that. So then you iterate always over the small set when intersecting sets. You always ask the sets, how big are you, before you do anything, okay? Don't just say, oh, I'm taking the left argument of my intersection as the one to iterate over. Whoa, you're dead. So don't do that. Nested iteration over variables in the query in any order without any preprocessing, okay? And so the order here has to be the same order as for the dictionary, okay? 10 minutes. So proof optimality is constructive in general. Yes?
But if you could compute the intersection faster than by iterating over one set,
Yes.
then you could get some different algorithms. Like
Absolutely. That would be even better. Yes. If you come up with that, let me know. Okay. Yes. Yeah. So basically, but it's information theoretical. It's not impossible. There is certain scenarios where you have certain structured sets of sets, and where you can basically do this faster than just by iterating over the smaller set. Yes, but that's a very special case. It's the only cases I know where you can do it faster than just iterating over all the elements in one set. Okay.
if you have some balance, some search tree implementation of
Does it?
these,
Yeah, but yeah.
then the other points would
Yeah. Search implementation will actually be too slow here, because you get actually a logarithmic slowdown and lookups, and so also practically this is not a good idea. But you don't change the problem of actually having to iterate over one set. Okay, if you use a balanced search tree, at least if I understand you right. So okay, so there is some kind of stuff that took us years to figure out. So in other words, it's literally. Basically proving this worst case optimal is by using amortized complexity analysis with ghost data. So who's actually seen amortized complexity analysis in algorithms class? Oh, yes, thank you. So that's basically how we do it. Okay, so here's the algorithm, and it's actually not much going on. So instead of doing that, I'll take as an example again our query, our triangles, and show the steps of how we systematically develop the nested loop, okay? So we start off with the triangles, that's them up there, okay? The first step we have to do is make sure that the variables occur in the same order. So that means that the last one is in the wrong order, so if you take x1, x2, x3, so we just compute in the first part the set of all pairs in the other order. So that's the transpose of the relation. Remember, that was actually in there in the code. Once we've done that, we'll actually have to compute for a number of x's, but that's important, not too many x's, so not too many x1s, the x2, x3 that are related to it, okay? Look at the formula, that's easy. For a given x1, it's just by saying well, we need a relation, which is a dictionary, that says for a fixed x1, I still have a relation of the x2s that are related to it. Here there is no x1 in there, so it's still the relation x2, x3, original relation. And here there's an x1 in there, so we just get the x3, okay? So look at this one, set theoretically, you'll figure out. The question is for which x1 do we have to do it? And that's where the trick comes in. We'll look at the dictionary here and the dictionary there, and it turns out that only elements that occur in both of them will end up in the result. But we'll just ask which one of you is smallest. And that's what we iterate over. So we'll compute this for the smallest set, whether it's this one or that one. And that's data dependent, okay? It's input dependent. So you can fix it. And then we'll just continue doing this one, okay? So for each x1, we'll go through this x2s that are related to it. And you can literally just work it out by these formulae. And these formulae, if you look very hard, are reflected in the code here. Now, who has been waiting for Haskell? All right, there it is, okay? So, yeah, I have to admit that I like Haskell as a language to write programs in. I'm not sure I can read it so well. Okay, so that's it, okay? So you can see now any kind of join query with more than just 2 arguments, with more conjuncts, can be treated this way. Doesn't have to be cyclic, it also works well. Cyclic is a certain notion of nasty thing that makes it hard for regular data processors to work well, okay? So let me wrap up, okay? I'm getting there. So I'll go have a detailed proof. I don't know, you said it was 25 minutes, right? 5 minutes, okay, yeah. So, simple joins, worst case optimal, okay? Here's a sketch of the proof. As I said, it took a lot of time, okay, this is a completely new proof of worst case optimality for those of people who have actually looked at the algebraic combinatory geometry proofs. So, let's make some observations. The worst case output size for triangle query is in general n to the 3/2. But as it turns out, it could be less, right? So for the Alice set, that's the maximum, right? So for the Alice set, it turns out it's always linear, okay? And it turns out that because the Alice set has a nice structure, which can be explained in terms of the proof, the algorithm exploits this structure, so it actually only runs in O of n time, not in O of n 3/2, like DuckDB does. All right, so I have to compare this. There's this famous work on what's called now generic join, and how is this related? So if you look at it carefully, we'll see simple join is simply a simplified version of generic join, where you just skip one step. So we just don't do number 5, okay? That's it, right? So the proof, blows out of the water that they have, but we have our own proof now, okay, that does that. All right. Is that the end of the story? I mean, you could say, hey, 0.02 seconds, that's fast, right? Come on, guys, we're computer scientists. That's very slow. So let's see, can we use, so for example, there's more optimizations you can play with, and you can implement if you know the techniques. It's not about coding, it's about knowing the techniques for doing this. So for so-called acyclic join techniques, there's a notion of reduction, full reduction. You can basically say at every one of those steps, remember that we have a query really again. You can look at it, that query before was cyclic, now it's not acyclic anymore. And it's not cyclic, it's acyclic. So we can use some of these optimization techniques. So we can use symbolic Cartesian products to represent relations. Very important, okay? So we are used to, in database systems, to think of representing a relation as a sequence or enumeration of tuples, right? That's really, really a bad idea, okay? A more general, actually very useful idea is that it's really a union of Cartesian products that correspond to the number of tuples, okay? Of sets. So if every one of those sets here is a singleton, that's exactly what an enumeration of tuples corresponds to. But now we have the possibility of having things here like are not singletons, like whole sets. Okay. So this is a very simple way of taking asking, please compute the paths. Remember, this is the paths. There's quadratically many of them. But then you say, oh, wait a minute, give me the count, okay? And it'll compute in linear time. Even though the output is quadratic, it'll compute in linear time the count. Because it just counts this, then it counts that, that's 1, and it counts that, multiplies them together, and adds them together here. That's it, okay? So we can exploit so-called low-rank symbolic Cartesian product representation to actually get this even faster by recognizing the input has this wonderful structure that can be written down in this form. So if somebody writes it down in this form, this will run even faster. And we parallelize, we can generate GPU, and we can use generalized, that's not, we haven't explored that yet, that's work we did many decades ago, that's how old I am. So, okay. So let's finish up. The secret sauce, and I shouldn't show this, is that the background is finite relational calculus, algebraic structures, and then the recipe we've employed is like embed the given structures you have. Here's finite relations, and into these rich mathematical spaces. And algebras exploit these algebraic properties for efficient symbolic computation at runtime, and map the result back to the original structure. And then, this is I've learned actually recently, not too long ago. Hide what you've done, okay? You hide it. That's the only explanation I have for how we came up with this one, okay? And it's because that's what we did, okay? But I just violated. Please ignore this slide, okay? So summary, that was actually, Mike said, do build a nested dictionary for each input relation at the beginning. Same variable order in each dictionary must be built fast to return us its size in order one. It turns out Python has the built-in dictionary, has the right thing. It's amazing when I've discovered that. And I'm also done. Yes. And then intersect sets by iterating always over the smallest set, ask them, and write nested loop in chosen variable order. Your joiner will be worst case optimal unless you do something and deviate. Namely, don't use merge sort join, okay? That'll blow it up. You get an exponential, you get a quadratic blow up. Don't use only binary joins. Don't intersect sets without first ask how big they are. That's it. Thank you.
Thank you. We have time for 1 or 2 questions. Start here.
Well, I have more than one. First, may I see the slides? Will you post them online?
You can have it, yes.
Because I want to look at the math behind it.
Yes.
Second, does this only work for double joins with 3 terms? With
No.
Tables?
This is yeah. It works for any number, any join of this format, okay? Which is for all joins.
Yeah, I mean, this is a quick question because I didn't have time to think about
Yes.
it. But did you find any way to apply this to SLD resolution?
SLD resolution. Okay. So the immediate answer
or
is
SLG, if not,
okay.
even better.
Here's an obscure answer: is that in SLD resolution, okay, you usually have to have free equality, okay, so you do unifications, and that's not directly supported here. So you'll have to go to a CLP extension of this. We're kind of working on this. So out of the box, no. But the longer answer is, okay, is that we're working on keeping this performance for the ground terms. Think about it this way.
Yes.
And then actually, making sure it's adaptive in the sense that if you use symbolic reasoning, like, unification, you only pay for as much as you're using.
But actually the question is there any way to speed up SLD resolution beyond the naive unification search?
That's a cool question. I'm sure I'm going to get kicked out if I start.
We will see. So for the slides, we have already collected them and they will be put to the website, I guess, next to the video. Do we have any quick question left? Still have 2 minutes.
So who feels comfortable now to write efficient joins? Just, okay, use your favorite language. Yeah, cool, yes.
So you still can give the answer to this one if you want. If you can do it in 2 minutes.
No.
Then I think
I
you're
try
right.
to catch up afterwards.
I have a paper, but it's a little bit unrelated to this one. But it would be very interesting to combine those 2 techniques with each other. Okay, so basically having very efficient data structures for maintaining unification structures. Basically equalities between terms. Okay, yeah.
Thank you.
And let's thank Fritz again.
Yeah, thank you.
Yeah.